Thank you for the introduction. I'm not going to show slides. I'm learning to talk. I want to go through some history and end up with what I think are the problems of today. I published a paper in 1978, derived a formula for what is still the best theoretical lower bound for the binding energy of a nucleus, if anyone, or more strictly a many fermion system, if anyone knows what that is. And I got one person saying I was wrong, and 2 weeks later saying I was right, and he may be the only person who ever read the paper. This could be the most extreme example of a scientist stuck inside an ivory tower. I was rescued from that by one of the best scientists New Zealand's ever had, Athol Rafter. In the 1950s, he was a nuclear scientist, but working out how to measure radioactive carbon to see how old bones and pieces of wood were. It was a rapidly growing area of science in those days. But to test his methods, Athol was regularly dating carbon dioxide in the atmosphere to give him a benchmark against which to measure the other things. And to his surprise, carbon dioxide was getting older every year. That was quite fundamental, actually, because people had wondered if a growing use of coal and oil fuels was increasing carbon dioxide in the atmosphere. No one could measure carbon dioxide very accurately in those days. So Athol's radiocarbon measurement showed that it was increasing because it was getting older. The fossil carbon, the dead old carbon, was going up. And it was increasing. He could tell, after 2 or 3 years, he could tell it was increasing much faster than the Nobel Prize winner Svante Arrhenius had predicted 50 years earlier. And he was the person who really came out with the first understanding of how we could be heading for global warming of 2, 3, 4 or more degrees. So we knew this before we could measure carbon dioxide. It tells you something about the science, the diversity of different disciplines and how they can interact with each other. Sometimes, a nuclear physicist can tell us something about the atmosphere. In January 1957, there was an article in the Otago Daily Times reporting Athol, realizing that this meant we were warming the Earth and it would lead to melting of polar ice and future flooding that could destroy coastal cities all over the world. That was back in 1957. It's on record. Well, I'm a slow follower of Athol, a guy I love very much, and I moved into climate science in 1980. And I came from that as a theoretical scientist originally, that's where my PhD was, with the misconception that this would be much easier problems to solve. What a mistake that was. To continue what Athol had started up, there was a group of us in DSIR in Gracefield who wanted to measure the heavy Earth's light isotopes, just like carbon-14 and carbon, was in other trace gases in the atmosphere. We were working alongside nuclear physicists who were coming up with ways of actually measuring the carbon isotopes in very small amounts using things called accelerator mass spectrometers. So it was a timely coincidence of having two groups of people working together in the same building, basically, and finding a way to work together. So we're the first people to reliably work out the fraction of old carbon in atmospheric methane, the second most important greenhouse gas. And we found it was twice as much as had been expected. That means the fossil fuel sources of methane, like from leakage of gas wells and things like that, was a lot more than people had expected for many years. We then moved on to doing it for measuring carbon isotopes in carbon monoxide, which is a much smaller concentration in the atmosphere than the methane. But this is becoming the best way of monitoring complex forms of atmospheric chemistry, keeping the air clean. And we've been struggling to get a paper into Nature in the last couple of years, and hopefully we're going to get it off in the next month, because we have 30 years of unique data. So we've been getting better at measuring what's happening in our atmosphere and in the environment generally, but now the issue is, does it lead to better care for the environment that we live in? Will people move away from the burning of fossil fuels, which we've known for a long, long time is not the thing to do? Some say science is about carrying out repeatable experiments to test our theories. But here's the thing from a science perspective. What we're dealing with is a once-only experiment. It's the same for many other structural changes we're making in our global environment. We only get a chance to do it once, and we'll learn as we do it, but it moves on to a different approach in science. So part of my learning curve in all of this was moving into the Intergovernmental Panel on Climate Change in 2002 and working with Susan Solomon to put together a fourth assessment report to governments. That worked across a range of disciplines to identify what's known and how climate changes and its effects, and how rapid uptake of technology could help. We won the Nobel Peace Prize in 2007 along with Al Gore. But a bigger achievement from the science perspective was to develop a cross-disciplinary approach to dealing with uncertainties in science. A colleague in Paris, Michel Petit, and I wrote an uncertainty guidance note for the authors. It came out of a very productive conference hosted by the Irish government. It still took us 18 months to get a wide agreement on how science should address uncertainties when we're dealing with things like a once-only experiment. As a little aside here, when I was doing my PhD in Canada, I discovered the journal called Irreproducible Results, which is a magazine full of stories that are all jokes made up about the science, about things that couldn't really happen, but maybe it happened once and it was irreproducible. But that's today's reality. We are dealing with an irreproducible experiment with our planet. Our uncertainty guidance note had to recognize then that science is dealing with different levels of confidence in our understanding of the science. How complete is the science? A confidence thing. And also, we use the term likelihood to avoid the word probability, because probability implies that you know the full range, everything, and you can say some is more likely than the other. Likelihood involves expert judgment. And so we brought that in, and it's being used in the both the next two IPCC assessments. It seems to be well established, being used by several other national reports as well. What's all that got to do with the title of my talk? Title of my talk, by the way, was Science of the People, by the People, for the People. Well, science needs to evolve in ways that improve the future for society, and it's got a growing urgency in all areas of earth science. The Paris Agreement of the United Nations Framework Convention on Climate Change agreed to keep global warming well below 2 degrees. But how many people know we're not on track with our use of fossil fuels to get there? And how many of those that know that feel there's nothing they can do about it, make it any better? That's the sort of problem we're in. We have to have a collective engagement. How many people know that sea level around New Zealand has gone up by 150 millimetres in the last 30 years? And that's more than the global average, a bit more. Then that information is there in gigabytes of stuff on websites, if you know how to extract it and look at it. It's not coming out. We're not putting it in front of people. There's a communication gap going on here. So science of the people needs wider forms of communication, ways that get information into the minds of some who would rather look at bargains in shops or work out what horses to bet on. We've got to get to those people. Explaining why what is being observed is important for them as well as everyone, and doing it in ways that can be followed. I'm lead author on a talk that's going to be presented in Vienna in a few hours' time by a colleague of mine. It's about a record rate of increase in methane that's been going on now for more than 10 years. And we show how methane is now making it much harder to keep to the Paris Agreement. Again, that's something that is not really out there very much. Science by the people needs things like our agricultural community to take up a more proactive role, to recognise that both methane and carbon dioxide are serious problems, and keeping below 2 degrees requires both of them to be significantly reduced. It's not one or the other at all. It's absolutely both of them. Methane doesn't have to go to zero, and CO2 does, but methane has to be reduced. Otherwise, there's no analysis globally that would say we'd keep to 2 degrees. I've been working for nearly 3 years on a plan for Cavity to deal with sea level rise. One of the most significant things we've done was talk to college students. They clearly recognise that they're going to live in a different world to their parents. It's happening. It's starting, and it's important. We asked some questions, and when asked how they would like to live with water rising up around them, would they retreat or would they live with the water? We were surprised. Most of them wanted to live with the water. They'll find a way. They'll have boats and raised houses or something like that. I don't know. It shows, I think, that young people are going to come in with new ideas. The science for the people needs to recognise how to work with the intergenerational responsibility. Young people can be very innovative. Maybe they won't get everything right straight away, but they have new ideas. We need to set up ways in which long-term planning involves those who will be there when the plans take effect. It needs more engagement of people in secondary schools. We found it productive. And I want to end with Al Rafter's 1950s comment about climate change, destroying cities around the world, and say we just have to help our grandchildren prove he was wrong. Thank you.
Congratulations again, long overdue. And I just want to recognise on behalf of the climate science community, and I'm a geologist who masquerades as a climate scientist, just to say thank you for your leadership. You were out there making us all aware of it before people really knew what climate change was all about. And it's great to see this and the climate community being recognised in this way. So yeah, just really want to say that. Want to challenge you on the irreducibility of the experiment, because you know I am a geologist.
Yeah.
And we have had warm climates in the past. We have had rapid spikes of methane and CO2.
Yeah.
But the difference is we went around.
I know. And as I think we've mentioned, we know about those things that happened prior to the last ice age when the planet was warm, but we don't know enough about the rate at which it happened. We know sea level was at least, let's say 6 metres higher, but we don't know how much it changed in a century. And that's the critical thing to know now. If we could extract that somehow from the paleo data, it would be a breakthrough. Thank you. Well, local governments have got a planning framework set by the Ministry for Environment, which talks of going to, in a century there are different scenarios, and we have to look at the whole range. If we were to keep below 2 degrees, which I've said is getting harder, we hope we would keep down to maybe 0.5 metre of sea level rise. But if we don't, and if things go wrong, and if there's a destabilisation of ice sheets, we could be looking at well over 1 metre. And the IPCC report came out with the upper scenario. Well, it came out with a whole range of high scenarios, but the one that gets most frequently cited and is in the summary for policymakers approved line by line by government, had one going to 1.6 metres. 1.6 or 1.65, I can't remember. We're now having some people say, well, we don't think that's going to happen. And so we're actually getting local governments retract from the science. And that's why there's a science communication problem here. We really need that engagement going in. It's not there yet.